The parametric form for rectangular hyperbola, so we have xy equals c squared was where we left off, and this was the hyperbola looking like this, with cc being this point here. And so what I want is to generate a parametric form for that. The parametric form is simply x is equal to ct and y is equal to c on t. And you can see that if you multiply these two together, you end up with c squared. Okay, so now we might go have a look at doing some equations of tangents and normals in the parametric form. So if we start with xy equals c squared, and if we use some implicit differentiation, then we'll use the product rule. So I'll differentiate the first times by the second, then I'll differentiate the second, which is dy dx, and times by the first, differentiate c squared, I get 0. Continue working with that, gives me dy dx is equal to negative y on x. So if I take a point P, and I call it x1, y1, and I say I want to find the equation of the tangent at that point, then I'll be able to say the gradient then is going to be negative y1 on x1. And so I'll go through like normal and go y minus y1 is equal to mx minus x1. In this case I've already got y1 and x1 in there, so y minus y1 is equal to negative y1 on x1, lots of x minus x1. This becomes x1y minus x1y1 is equal to negative y1x plus y1x1. And now what I'll do is I'll just move the variables x and y together, so I'll get y1x plus x1y is equal to, bring this over to here, gives me two lots of x1, y1. Remembering x1 and y1 lie on the line, xy equals c squared, that gives me down here then that x1 and y1 are in fact c squared, so I get 2c squared. That's the equation of the tangent at the point x1, y1. What I want you to do now is I want to practice this yourself, and I want you to run through the same process from start to finish. Don't take any shortcuts, differentiate implicitly and so on. And I want you to run and find the normal, and what I want you to come to in the normal is that x1 x minus y1 y is equal to x1 squared minus y1 squared. So do that for homework and be prepared to show me next lesson. Alright, so far we've done it for the Cartesian form for tangent and normal. I just want to look at the parametric form. And with the parametric form, what I mean is rather than implicit differentiation, we'll start with the point x equals ct. We'll say y is equal to c on t, which means it's equal to ct to the negative 1. And then what we'll do is we'll actually go and use dx dt is equal to c, dy dt is going to equal negative c on t squared. And then dy dx is going to be equal to dy dt times dt dx, which is negative c on t squared times 1 on c, which gives me negative 1 on t squared. So that's my gradient. Oh, sorry, that's actually dy dx. Now, if I say the parametric point is at a point P, which is CP, C on P, then to get the tangent, I'll first get the gradient, and I'll say T has now become P, so I get negative 1 on P squared, and I'll go y minus y1, which is C on P, is equal to m, negative 1 on P squared, x minus CP. So I'll multiply everything by p squared y minus cp is equal to negative x plus cp. And then I'll just bring these together and I'll get x plus p squared y is equal to 2cp. So that's kind of nice and neat. Alright, the normal is even easier. I'll get you to do the normal yourself, run through it, and see there's really only one step involved in it. See if you can come up with px minus y on p is equal to c p squared minus 1 on p squared. See if you can come to that with the normal. Okay, just a quick look at equation of a chord joining these 2 points in parametric form. So to get the equation of a chord, I just want to establish the gradient as being the difference between the points. So the gradient is just going to be c on p minus c on q all over cp minus cq, y2 minus y1, x2 minus x1. C can be cancelled there, leaving me with, if you have a look at what you've got there, cross multiplying, I've got q minus p on pq all over p minus q. So this is just the negative of that, so when I divide I simply get negative 1 over pq. So that's the gradient of the chord. To get the equation of the chord, rather than going y minus y1, I'm actually going to use this idea. I'm going to use the fact that the chord is a straight line, so it can be expressed as y equals mx plus b. And what I'm going to do is I'm going to sub that gradient in there. Y equals negative 1 on pqx plus b. Then I'm going to sub in the point p, cp, c on p to find b. So by doing this, I'll get c on p is equal to negative 1 on pq times cp plus b. See here the p's are going to cancel, so I'm going to end up with c on p plus c on q is equal to b. So continuing from that, I would get cq plus cp all on pq is equal to b. If I sub that back into my equation up here, I get y is equal to negative 1 on pqx plus cp plus cq on pq. Simplify it by timesing everything by pq, and while I'm there I'll bring this over to here. So I have x plus pqy is equal to, that's gone, c outside of p plus q. And that's the equation of the chord in parametric form. Now what I want you to do is I want you to repeat in Cartesian form using just the points x1, y1 and x2, y2. And when you repeat that, I want you to see if you can come up with as an equation, a little bit more complex and not quite as nice, but anyway, c squared x1 plus x1 x2y is equal to c squared outside of x1 plus x2. Okay. Just repeat what I've done and see if you can come up with that one.